Hello, in this video we'll be looking at diffraction, and in particular diffraction caused by a single slit diffraction. Okay, let's say we had a slit here. Okay, now a very thin slit, because we want it thin enough to cause light to be diffracted. And so we had a source of light here. Now, on average, the wavelength source of light, we often say in physics, it's around about 500 nanometers. Okay. Now, of course, doesn't need to be monochromatic light, but of the ranges of light, on average around about 500 nanometers. Now, if we have a source of light here, and it comes to a very thin slit, and you have across here, let's have a screen. What happens is you will get some diffraction patterns from the slit. And what you'll find, now let's draw in a line here representing the middle. And I'm going to make the slit larger, not because it is large, it is very small. It's just so that we can see what's happening. And we're going to call the slit width here is going to be, it's given by the letter B, that is a slit width. So light comes into this narrow slit of a similar order of magnitude in width to the wavelength of a light. And what we find is we will get some patterns. And here we'll have a central maximum, the most intense light, so there. And then what we'll find either side of it, we'll find some other diffraction patterns like that. So we will see slits on the screen, and these slits, and what you see these not slits on the screen, these light on the screen, and you'll notice that they're getting less intense as you move away from the middle. So if we now put a graph on there to represent the intensity, we'll find this is a central maximum, that is the most intense. Then the next one, like that, and it sort of fades away. So it goes the next one, and then kind of fades away. So that represents the intensity on how bright it is. So intensity. Now, what you will find is that where the minimums are, the minima is plural, minimum, you'll find that there and there, there and there and there, these appear dark. Okay, and if we were to take from the centre of the slit, then we're to draw a line to the first minimum and measure the angle there. And if we use radians, always use radians, we'll find for ourselves that the angle to the first minimum, theta, is equal to the wavelength of the light, which is 500 nanometers. And let's convert that into SI units. So that's 500 times 10 to the minus 500 times 10 to the minus 9 meters. That's a nano. Is equal to the wavelength divided by the slit width. That is to the first minimum. And to the second one, we'll find here that the angle would be the angle to the next one. So if we measure now the angle to the next one, the angle would be, got theta 1 and theta 2 would be equal to 2 lambda over b, etc., 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 etc. So in the whole pattern would be the angle theta n would be equal to n lambda over b, where n is an integer equals 1, 2, 3, etc., etc., etc. Okay, so let me just draw that in bold there. Okay, so that is the angle to the first minimum. Okay, now, so what are the effects of this diffraction? Well, the effects of this diffraction through small objects affects how the resolution and how well you can see small objects and giving off light sources. So that affects something known as resolution. And what we'll do is we'll look at resolution in the next video.